Right, when no, thankfully I started to cover spring break. I would have started this.
Dang, I'll be calling him out. Dang,
That's all I want to show.
figure it out.
I want to share my screen.
Now the Emag has been pushed back. I feel better. We still got circuits to think about.
So sharing that now.
97.
Yeah, let's do next week for right after the Emag test. Next week. Okay.
But no, actually, so luckily, I actually thought that our was Thursday instead of next Tuesday.
Oh, so you, okay.
So whenever people were talking in class like that, it was Tuesday.
So it was next Tuesday. He really asked, he goes, next Tuesday or Thursday? The whole class goes Thursday.
God damn it! I would have more time to prepare then.
Hey, if you want to move this to like Monday.
Nah, it's fine. I'm already here. I'm already kind of set up, so.
You know, because I was looking at the syllabus and I saw T. I was like, oh, Thursday. I know that T is having to.
Yeah.
I need to mute you.
So when people were talking about it in class, or asking about it, I was like. Now I went and looked, I was like, I should do that. I love what you did.
How else would you write Thursday? It's not TH.
So honestly, I don't know if I even realized that it was just T. I guess.
Because I am viewing it. Okay, so I don't really need this one then.
Like 30
Oh,
TH.
okay.
Maybe I like imagine the TH.
That one that I do need.
We're seeing shit. We're seeing shit.
This one.
I mean, he is an Emag, so must make sense.
Okay, so I can't see it on here. That's fine. I can
It
just
just worked like.
probably just. Well, that's going to.
Oh, it's like.
And I have just display on me. That's fine.
You're welcome. On my cheat. Because it's just shows impedance matching right there.
Mhm.
I thought there's a lot of space though.
I can a little bit.
I would put the last quiz, or like the that quiz.
But, yeah.
Yeah, as well, yeah.
That quiz was very difficult.
I'll need to watch what he did, because he did the shortcut and I didn't do the shortcut.
That shortcut only works if
Independent.
there's no real.
Oh, yeah, I know. Was no,
I thought
was it
you-
no real or no imaginary?
No real. Because the matches are trying to match, right?
Well,
Oh, you're right.
yeah, it's like with the, are we talking about like what?
What he did on the quiz.
The quiz, yeah, it's when your real, like the real part of your load is already matched to the real part of the line. You just have to change or figure out what, yeah.
What I done right here. I'm surprised he actually didn't go to quiz today.
Yeah.
What do you mean?
It's awesome.
Oh, yeah, no, I think he realized it's taking too much time.
Really?
Yeah, no. So the quiz, he gives us a quiz, right?
But he's going to give us the answer towards the end when he gave us that A omega sign.
Oh,
Can I borrow one?
but he gives us now in-person quizzes, right? And every single quiz thus far, when the quiz has been done, he's done the derivation right there. And like, I just had to do it.
That's good.
Derivation.
Oh, you said derivation.
Variation. What were we
Oh.
fucking curdling milk now?
Okay.
But
What's the change rate of milk?
Huh? Change rate of milk.
That's
No,
pretty good.
but he didn't do it this time, and I was like, he probably just realized how much time was taken, because he before, like, class starts at 12:30, but we wouldn't actually start lecture until like 1, so like full 30 minutes.
It's probably because it's just a chat or the lighting in here. I have to turn off the light because I can't change lighting on here on my own unless the remote's here somewhere, which I couldn't find it though. So
Yeah, I haven't seen that remote in a minute.
yeah, I haven't seen a remote either. So
It's this thing.
Well, then we can't get to it anyway.
Here's a mouse,
that's the Logitech.
a mouse.
Check behind the machines.
No, that's what I kind of assumed
Nope.
it was, but there's nothing back here. So
Yeah, my guess is in here.
Yeah, they probably slipped it in there
Yeah,
when they did the
there's
recording.
no-
I'm about to head out after finish up. the-
Alex is like, nah, it's gonna be.
Yeah. No, I'm not, I'm
I'll still-
class, so off work one hill.
And you were doing like, oh, so you do it like that, like, Alex, you're not.
all right.
I mean, if it helps, it helps.
Okay.
I'm here to eat.
Which is why I said,
It's-
oh,
I have 2 hours because I still gotta go into work at 6 tomorrow, so.
Jeez.
Yes, what problems do you guys wanna do? So I have a no diagram, stub matching, single stub impedance matching, okay? I have basically a physics problem, basically, using your quadratic equations and whatnot. I have a different single, not single, well, yeah, a single stub impedance matching question phrased a little bit differently, a little bit different.
Is there any way you can post these questions in the Emag Discord so we can see them closer up?
Sure. Those are not the ones I have.
I was gonna say, he's got a different test, I guess.
I have the goods.
Bro,
yeah.
that's a lot of unread email.
Yeah, no, it's fine. Yeah, sure. Just give me a second then.
This is 40K.
I didn't kind of get roasted for my emails,
I
okay?
was gonna say, we may or may not.
Yeah, I gotta get
You got 40K and 470 over there?
I know.
Oh man, we should.
I do read my emails at work, okay?
Do it.
Yes.
When was the last time you went to work?
Hey, you know this is recorded, right?
Yes, this is recorded. I'm just gonna crop it out.
Oh,
Yeah.
this one. Where does Paul? What?
Which one is it? Is it this one?
We found that right. Yeah, we heard that correctly.
This one?
You know this is recorded, right? You said that to her.
They couldn't hear me.
Probably.
We did.
I mean,
They, like,
yeah, but it's not that
That's
much
where the sound is being picked up.
No, it is. It's just I'm not
No, like
having it.
where?
Where? Right here.
Oh, okay, yeah, you're probably good.
let me check if it's there.
Is that a link or is that the actual PDF?
I'm about to check. That is the actual PDF.
Yay.
Thank you very much.
Welcome. Back to where I was going. Okay, so it's in the UEG Discord Emag chat. And then I have essentially a weird problem right here. This one was a fun one. There's a reason why it's worth 40 points. Is basically given S11, find your load.
Given us. Oh, we already did that.
Oh, yeah, we
That was our test.
Was it your test?
That was literally the second question over test.
Yeah, that's what you did last.
Can you read the second part though?
Okay.
Single stub impedance matching method is used to match the antenna with the impedance A, which are finally closest DM. I'm sorry. We didn't do the second part. We did the first part.
Exactly.
Example, right? I mean, the one from the book that we did for quiz.
Kind of. Kind of. It's very similar, a little bit different though. Because this really depends on how you're gonna approach finding DM, right? So.
Then do you want to start with this one?
And then there's also just a double load. Double loads are pretty easy though.
Double on. That's what we were ready for.
Double loads?
Yeah.
You sure?
Well,
No, on test one, him and I went over like 3 or 4 double loads,
Mhm.
expecting a double load, and just, we didn't get a double load.
Yeah.
So which problem do you want to cover first?
Uh,
That's one was like a warm up.
As a warm up?
It does not matter.
Does not matter. Let's just do the first one, honestly.
Okay.
Sounds great.
First one's pretty easy. Okay, so we're gonna actually draw it out first because I enjoy drawing this stuff out. Okay, so we're saying there's like some generator somewhere out in the world in free space. Who knows? Okay. Okay, and we're saying this ZA load is equal to 73 minus J27.5 ohms, right? To a intrinsic of 50 ohm transmission line, right? Okay, due to the nature, the transmission line segment within 0.7 lambda from the antenna is not accessible. So what does that mean? What does that mean exactly?
And due to the transmission line segment within,
0.7.
from the antenna. So the antenna at this point is the actual ZA, correct?
Yeah.
Yes, we are given our ZA load.
And that is,
So the distance that you put your stud at to it, greater than.
Exactly. So basically, at some point, assuming this is our reference, we're gonna go in the negative zone just because that's how I was taught to do this stuff. We're saying at some point, 0.7 lambda, we cannot use it.
We cannot
is
use what?
inaccessible. That distance closest, the 0.7 lambda with closest to the load is inaccessible. People get confused on the wording some days. That's why I'm here clarifying it. Within the transmission line segment closest to the antenna, right? 0.7 lambda is we cannot touch.
It basically means we can't put a single stub there.
Yes, no stub can be put there, right?
Okay.
But there is a way around it.
0.7 lambda, free for all.
Yeah. So what do you think is a good starting point here? What do you think is a good?
Finding gamma.
Exactly. You always find again. Always find your reflection coefficient first. So always find that first is a great starting point. Doesn't really trip up anyone really how to find gamma. So I'm not.
So ZA is our load impedance, correct?
Yes, is your load impedance. Let me actually write the equation down because I don't feel like doing the math because my calculator is in charge right now. That's fine, honestly. And also correct me for any of these equations too. Like I am very rusty on this stuff, but I still remember it pretty well by heart. I said zero, so just correct me at any point in time, okay?
We're giving this not.
Yeah.
We got 50, okay. Nope.
Yeah, okay. Now, from here, where can we go with gamma in terms of equations? Like, what you guys thinking?
You find
Because the goal is to find the stub, right? So
Yes.
what are we missing right now? Of course, we're missing some distance,
Yeah.
some distance min. Okay, we're missing that. We're definitely missing what are those other components whenever we try to stub match, right? Because there's
missing an angle.
we're missing an angle. We are missing that for sure. We're missing our theta. What else are we missing?
Missing a beta.
We're well, kind of.
Find beta.
Kind of. I'll list out there. We are forgetting for stub matching, it's typically ideal to find your absolute value of your gamma.
Oh.
It's typically
Magnitude, yes.
magnitude. What's that formula though?
Well, we're given, what do you call it? Gamma is given as magnitude of gamma e to the I theta gamma, or, yeah.
Yeah.
So it's just simply, if you take it in polar, it is simply the thing that is in front of the E. Did that make sense?
Just be careful about that. So depending on what you actually want to do. So like you mentioned that weird equation. I believe that's what it is. I can't remember what it is off the top of my head right now.
Never mind.
No, it's that why am I writing an F right now? E to the J omega B, right? Am I going crazy about that?
E to the J theta R, theta.
Theta R, yeah, my bad. DGA make theta R, or careful, you can also work in the rectangular form of it, right? Of just whatever that value is. Just be careful which form you do it in. Just make sure you're consistent about it, okay?
Yeah.
But basically, so once when you find gamma, what the magnitude of gamma? Where do you go from here? What's the next equation?
Wait, go back to the rectangular part of
Okay.
the magnitude of gamma.
Yep.
What is that in terms of rectangular components? Is that simply just the?
It's just the equate. It's just the whenever you guys were
Okay.
converting back and forth, it doesn't matter which one you use. Just stay consistent about it. Okay.
What you're
Okay.
saying is just the square root of squaring it.
Yeah.
I'm pretty sure, right? Just square root of x squared plus y squared.
Yeah, basically.
Okay,
Okay, cool. And X being the real, Y being the imaginary.
Yeah.
Yeah.
But don't include your k.
Exactly. Don't include the J. People get tripped up on that. It
Yeah.
may be needed though. Just depends on what else you might be asked, right? Just keep that in mind. So what actual equation do I use with the magnitude now?
Say that again?
What equation do I use to find using the magnitude?
Okay.
My bad. What's the next line of math there?
We can find the susceptance.
Which is?
It's 2 magnitude of gamma, times, sine theta over 1 plus magnitude of gamma squared plus 2 magnitude of gamma.
Oh, the long equation.
Yeah.
There's a shorter path though.
There is.
There is a shorter path.
Oh, free the teeth.
There's a shorter path because the biggest thing is right because in the book it covers a very long convoluted path of like find your admittance first and then go through find your other stuff there, find your length and your BS DS, right?
Yeah.
The real equation you really want to use is basically But also double check in the book though. Explain to me why this equation works.
Wait, shouldn't that be the angle?
It is.
And what is that? I'm sorry, that says,
What is on the left side of the equal sign?
TJ?
Yeah.
what does DS stand for?
DS stands for your distance of, I believe it was not your minutes,
It's like the sh-
the shunt. Yeah, distance of the shunt, basically, of how far away you're gonna be getting it. But you're right, I did skip finding theta R. You're right about that, my bad. We rearrange equations around.
Yeah.
Yeah, I did skip it.
Yes, yeah, wait, what are you?
Go up a little.
Oh, that one right there. Oh, no, no, no.
Okay, I'm gonna be going back and forth, okay? I'll be going to.
You're right, my bad.
Did you took the inverse cosine of negative magnitude gamma?
Yes.
That is the theta.
Is that for theta?
Yeah.
Okay.
In the book, that's theta.
Is that what they use in the book still?
Yeah.
Okay, I'm going crazy about that.
So theta, you need theta and theta R.
I need theta and theta R. Yes, my bad. That's the step I always forget. Apologies about that. Yeah.
Yeah, theta prime.
Okay, so
Yeah, because
we're gonna make a list now.
We'll be given two thetas.
Yeah, we're making a list. Okay, so 1. Okay, always find your reflection. It's a great start. It's a good starting point. Find it. Okay. Always recommend it because you can work with this in basically any equation. 2. In this case, for stub matching, you typically want to find your magnitude, okay? Your magnitude, just careful on which form you're going to be using. If it's polar or rectangular, just be careful about it. Stay conscious of it. Understand how to work with both of it, right? The next step will be finding your theta R and your theta prime, right? So then which one do I actually find first? Theta prime or theta R?
Theta R would be easier.
Theta R will be easier.
Just angle over here.
It's just the angle of it, yeah.
That if we were to use rectangular, would you just recommend put it in polar?
Tangent.
Polar is typically easier, in my opinion, for this stuff specifically. Rectangular, I've seen people work with it, is just a little finicky to work with the math, because especially with the Inspire, you might fat finger something. So I just like the magnitude EX, yeah.
Why are we not normalizing it into admittance?
So
Because I thought that's where we wanted to start. We wanted to normalize it to admittance. Then from there, we can find the reflection coefficient in admittance. And then we start finding our theta prime and all that stuff. So why are we not doing that? Is that something that you're gonna do towards the end?
So it's not necessarily needed as much. Well, okay, let me rephrase that. You would be correct. Most students do that. I used to do that, right? It's just an extra step you do at the very end. To basically in inverse with J is just doing that J manipulation. People trip up on a bit.
What did you ask?
She's asking why we didn't convert this into admittance first. So the Z naught over ZL, I believe. Yeah, Z naught over ZL to get your Y value, right? Then from there, using that to find your gamma.
That's how we did it. That's how we did it on the homework. So I'm just.
And that's completely fine too. It's completely fine. It's just at the very end, whenever you're gonna be finding your it's just manipulating that last equation, whichever form you're using with. If it's normalized already to admittance, you can use what the book shows you. If you didn't normalize it, you have to do some quick math there to basically manipulate it again.
So if we're not normalizing it,
Mhm.
right, towards the end,
Mhm.
we have to normalize it again?
Not normalize it, but just change it to. How would I explain that? The book shows it normalized, right?
Correct.
If you were to use the same equation again with just regular gamma, not your admittance gamma, right?
Okay.
The math would be incorrect. But if you know how to manipulate the J factor, it would correct itself. It's specifically that J factor that where all this really comes back down to.
Do you want to see the
I
book?
guess I just haven't seen it not normalized.
Exactly. No, yeah. The book doesn't show that. The book doesn't show that.
J
Yes.
in the book.
Mhm.
So when you're talking about the J, to me, that's like what? we're, even to watch it, he normalized it too. So I guess I'm just wondering how you're approaching this problem.
I'll show you that line of math and explain where exactly you would just do a quick correction.
Okay.
Do you want me to show you real
No,
quick?
no, I want him to teach. I mean, this is from the book.
What is theta prime? What is that?
Theta prime is just really a factor, if I'm remembering it correctly. Okay, basically here, let's actually write down the actual equation. Theta prime is,
I've used all the time. I think what it is.
yeah,
Right, over here,
They
they
norm-
used this, right? And so they said that the
Right.
impedance of that thing was.
Like I know the formula, but like what is it?
back to trig. So you know how,
Reflection angle would be like here.
yes,
And then so it's like just the opposite angle.
basically.
Okay, okay.
Basically,
okay.
because yeah, that's all it is. There's a reason why, if you're not careful, if you use like, for example, finding B naught using tangent versus the sine and cosine equation, you might have to shift your tangent into an acceptable region, right? It's just minor things like that that the book doesn't explain as well, which is why I like and dislike this book.
Can't resolve an issue.
Yeah.
What is theta prime? Cool.
And what was your answer?
Tangent line at a magnet, at an angle, like that, right?
Exactly.
Yeah.
Yeah,
Yeah.
Okay.
No,
yeah.
Yeah.
This is the in.
Okay, but we can put some values down if you want, just so that we can like actually show what you should be getting, because I have plenty of values. I just didn't actually be able to like write down all over the math because I'm tired. Okay, but basically, so assuming you did step one, your gamma should come out to be a very, I'm gonna provide a lot of significant digits just because that's how I was. Because I put like a float of like 7 on my calculator. So it's your call what you want to use, what you want to do here, okay? But I can work out the math later, and if you still have questions about it, by all means, shoot me a email.
The magnitude of the gamma is 20,000.
28.28.
Huh? Oh, the magnitude.
Oh, 0.28? Okay, okay. Thank you.
Yeah, I just write with a small pen on my iPad.
Sorry.
Yeah, no worries. Okay. Okay. Again, I'm skipping a lot of the actual legwork and setting up like the actual thing, but visually speaking, though, you guys should be still familiar with this because all you're doing is finding gamma first, which is just ZO minus Z naught over ZO plus Z naught, right? Then you're gonna find a magnitude. Let me find the actual equation for the magnitude because I don't feel comfortable not leaving that in.
Well, you're talking about the rectangular thing, right?
Yes.
Which you like, well, like we were talking about, you would square the real part and square the imaginary part, add them together. Square root of that. The square root of the square of the imaginary plus the square of the real.
I think so.
It's just,
That?
like, it's like finding the magnitude for a vector, right? I
Yeah,
mean,
yeah.
that makes the most sense. Like, as he said that to me, I was like, oh, yeah. That
No,
makes sense.
yeah. That's what it is. I just want to see what the book says again because I was looking at the book earlier today as I was driving over here. I just want to make sure that that's what the book also encourages. Yeah, no, like I said,
He's got
okay.
stoplights on his way.
I've done that too.
I've been
I can't say it.
up since 4, my guy.
Some of these circuits tests are early in the morning. We gotta flip through. It's usually my notes.
If that's what you're going on about, dang, okay.
Hey, I was, there's 6 of us.
Okay.
Maybe switch the song.
It's called multifaceted, okay?
Then men cannot say that they don't multitask.
I never said, I never said.
Are you a man that said that?
I'm not a man.
Are
who said
you,
that.
are you a man that said that?
That's sort of the rule. I think it's a
Yeah.
multitask.
I don't know what man said that.
Did I write that first equation down?
Yeah, you? Are you
First
a man that says that you can't multitask?
Yeah, he's really trying to put a point in it.
Depends on what I'm multitask.
That's a yes.
That's a no.
That's a yes. Anyways, answer back to you.
Yeah, no, I'm just double checking something. Okay.
He's multitasking right now.
Yeah, no, so I'm gonna reference the equation of the book, right? Not that many people because I didn't actually send the team's invite out by accident. I forgot to do that.
Oh, sweet.
Do you only drop it in the IEEE?
I mean, it's just in the HTN thing, so it's gonna get recorded there either way.
So people are smart.
This is live. This is getting recorded. It's just I don't believe I have an audience right now online. Anywho, okay. Yeah, no worries, no worries. Okay. Okay. Yeah. So you need to find, so again, we're gonna restate the steps, okay? You're given this weird problem, you're given a load, you know your intrinsic impedance, which is just 50 ohms normally, and then you're given a section of where your stub cannot go, okay? So you're still gonna be assuming you're gonna be finding some sort of load value, right? The biggest thing is you just have to keep on going until you find your distance. Okay, and we're gonna approach that slowly.
Oh, the end times, is this where the end times comes in?
We're gonna get to
Okay.
it. Let me just actually write down a few more values one last time.
Yeah, the number of.
Yeah. Okay.
Wait, did you write down the formula for theta R?
No, not yet. No, that's why I was gonna correct it here.
I'll ignore me, I'll shut up.
That's what I was trying to find in a book right now because I could have sworn the book references it, but if it doesn't, then
No, ignore me.
No, I'm asking, Francis, if that's what he put for the end times.
now I'm looking for theta R.
Okay,
What are you looking for theta R?
Just actual equation for it.
It's theta prime equals theta R.
no, he's trying to find theta R.
Theta R, the value of it.
Yeah,
Well,
not.
No, isn't it
not
just
the-
put your reflection coefficient into polar form,
That's what it is.
whatever that.
That's what it is. Yes.
Yeah.
That's why I like the polar form. That's why I remember now. Yeah.
And then the magnitude of it is also whatever.
Whatever it is.
You just put it into polar, the magnitude. is
Yeah.
the Thing on the.
Now I remember why I like the polar form now. That's exactly the reason why, because it's just like look at it, it's just like, oh look, there's your theta R. It's amazing. But just to clarify, reason why I encourage people using the polar form is because that theta value up there is your theta R. Okay, because and to find it given your rectangular form, if you were to choose to do it, is just straight up just doing that not square root, yeah.
What?
The tangent of it basically, yeah.
Got it.
Or it'd be the inverse tangent.
It would be the yeah, it'd be
Inverse tangent of y over x.
y over x, yeah, to get that theta value. But again, it's just weird math stuff that the book doesn't cover, Death Watch doesn't cover. It's just a little. It's I just like it a lot, but it is what it is. Okay. The fourth thing you probably want to do after this is finding your stub, your distance of your stub value. Okay, and that's where that cosine value I wrote earlier is, because typically in the book you're going to see it as
See why we need the 0.7 and everything.
Theta prime equals negative of your gamma.
yeah. This is where I wrote that earlier, and then your DS is going to change into not your DS.
But then
Yeah,
there you can find,
theta prime. This is theta prime. I'm crazy.
yeah, theta.
Yeah. This is what it is. Cosine inverse of your negative magnitude of your reflection, all right? Now you get two values. Yes, this is positive or negative of your theta prime, right? You get two values you can test, okay? And I will cover how you use those here in a bit. Okay, now, how do we actually use that? Like, what equation would I be plugging in these theta prime values into?
So into the imaginary, if I'm not mistaken.
Sorry.
It's very similar to what you were going with. Is just
Oh, yeah, that's in the book.
yeah, no, it okay, because the book shows you basically a very long derivation of what it expects you to understand, right?
Yeah.
But the biggest thing is we really look only at the real components because that's what we're physically putting there.
I thought,
If you do the admittance. No, but okay. No,
Okay.
I'll work with you, okay? I'll work with you.
So if you normalize,
Yeah.
the watcher in the book normalize it to admittance.
Mhm.
When you're normalizing to admittance,
Yeah.
then once you're trying to find that distance, this part is what you're looking for the imaginary. He didn't do that, therefore we don't look at that,
Mhm.
and that's why I'm still, I was.
No, that's why she's getting upset with me right now, yes.
That's why I was like,
I'll tell you why it's an admittance, because it's in parallel, so it's easy to add an admittance. An impedance, you have to do the whole formula. That's why everyone switches to admittance, so you can just add it straight across.
Yeah.
Yeah.
Okay.
That's why they use admittance.
okay,
You know, in circuits one, like admittance, you can add in parallel.
Hey, we're gonna speed up a little bit though, because I do want to touch bases on the other problems. So, real quick, we're at step 3 right now. We found theta prime. There's 2 values you get out of it, right? Okay.
Positive and negative.
A positive and negative. You would have to test both no matter what.
Yep.
Okay. To get using that distance equation, where basically it's lambda over 4 pi of theta r minus whichever theta prime value you're going to be putting it, right? Okay. So now we have 2 distances we have to test, right?
Yeah.
Those 2 distances, you can easily tell by inspection if they're within the limit
Yep.
of what we're allowed to use, right? So right now we're saying we have to get a value greater than that 0.7 right there, right? Because this is what we would claim to do, right? And just to show you, this I did do some of the pre-math for, so I'm gonna claim it's negative lambda.
Send it. I don't know who you're sending it to, but
So you said D1 is negative 0.2.
0.0021. Yeah.
Lambda.
Oh, it is a little large, so that's like that. Okay.
D2 is 0.0959.
Yes.
I'm trying.
So
the-
you said you're going in the negative direction, right? Because that's how, so would you use the negative distance here?
It's really more so just as
I thought D was supposed to be positive.
D is supposed to be
negative
positive.
L, right?
D is supposed to be positive.
Yeah.
The negative thing is more so for a frame of reference, right? Because the only place where it would actually get canceled out would be here.
Okay,
They-
okay,
know?
yeah, I see it now.
That's the only real place where it would get canceled out for that negative sign. So just keeping that aware, right?
Sounds good.
Yeah, okay. Now, I have 2 distances, okay? I have 2 distances. What do I do? Because they're both within the range of what I legally can do, right? One's going to the right of it,
Yeah.
one's still within the range. How do I shift this around?
Like within the range, you mean like it's too close?
As in like, yeah, so physically distance 1 right now,
Mhm.
we're saying it's on the right-hand side.
Yeah, so you're saying that since you use the negative direction, as in your 0.7 lambda is now negative 0.7 lambda because you've moved in the negative direction.
Yes.
Okay, cool. So,
Yeah, so I'll draw out what this physically is right now,
Okay.
okay? I'll draw this to show real quick.
been sitting in the chair for a while.
Yeah.
Is that uncomfortable like seat?
Okay, so what's going on right now is basically these 2 values aren't good, okay? Because we're saying if we were to work with these values on its own right now, we're saying, hey, guess what? This D1 is staying somewhere over here, where at some point we have the 0.20021 lambda, and the distance 2 is just barely over here, right? It's not to scale, obviously. Don't consider scale, just consider the value.
But now I'm kind of confused
I am too.
because you said that we said like at the position of the load, right?
Mhm.
The 0.7 lambda was going in the negative direction.
Yeah.
Right? So I thought that D1 would be in the direction of that lambda.
He switched it
Because-
back.
Because D equals negative L. You
You
remember
mean
that?
D equals negative Z?
No,
Negative L, right?
yeah,
Negative L, not Z. Or I think, I don't remember the Z part.
D equals negative L. And D and L
Are they in the same direction?
are in the same direction.
Are they?
did I flip this then by accident?
Did I?
Because
I don't believe I did, no.
Let's check.
Okay,
Because you could 100% be right.
Because I've seen
Okay.
formulas where they've used D.
it depends your frame of reference. It's the biggest thing, right? So we're claiming right now, we claimed in our original thing where I'm saying I'm traveling towards the load or towards our generator, saying that's in the negative direction, right?
Towards is, okay, yes, okay, yes, okay,
Yeah.
cool, yes.
That's the frame of reference I'm always gonna use for these problems, right?
Yes.
Yeah, so that's what we're saying right now, okay?
And that is using, in terms of L's and Z's or whatever, that's using the Z part.
Yeah.
That's using the Z reference.
Yes.
Got it.
Sorry. That one more time.
So basically, okay, because of my frame of reference, I'm claiming traveling towards the generator is in a negative length, okay? Because of that reason, whenever you go and actually calculate this stuff, whenever wherever you find in beta, you plug in 2 pi over lambda, right? That negative lambda is going to cancel a lot of things, which is why this frame of reference is indicating this value, where I'm saying the negative is literally going to the right. I'm saying this negative 0.20021 lambda is off my transmission line. And then this distance 2 is still within an inaccessible region. One's imaginary, basically. I can't physically do anything there. One, I'm restricted, okay? Well, what can I do? I can shift it in, but how do I do that? Exactly.
Why would it be lambda over 2? I'm
Be-
just curious.
because of how cosine works. But not cosine.
Sorry. Tangent?
You're supposed to increase the angle.
You don't increase the angle. That's the long one. Because that's what you're doing is technically just shifting it over by pi over, or yeah.
Yeah, because impedances repeat every lambda over 2 because it's of inverse tangent or tangent, yeah.
Hmm.
Inverse tangent or tangent.
Makes sense.
Yeah, okay. Basically,
This.
okay. So what we're saying is we're going to shift in our answer by pi over lambda, okay? Why? It's because it goes back to your trigonometric functions of how it will repeat itself at every half wavelength, right? He may have not covered that directly, but that's technically what we're doing. We're just kind of transforming it in a sense to shift it over at another value where we're going to get the same impedance, not same impedance, another acceptable value to where if we use this distance here, it's going to get the same impedance. And it's going to repeat over and over and over, right? Which is what it comes back to, like the whole unit circle and stuff. But so that's what we're gonna do. Okay, we're going to shift over both of these by if I can. Other way around. I'm crazy. Land over 2, my bad. A half wavelength. Yeah, I'm crazy. I'm crazy. I was saying like pi over land or yeah, no, my bad. Apologies about that. I'm just like that's not what I wanted to do. Okay.
The distance thing, right?
Yes.
In my mind, I'm thinking it's the other way, where the negative goes in towards the generator and the positive goes the other way.
This honestly is more of like a frame of reference issue, right?
Yes.
In reality, this doesn't really matter.
Wait.
It does not matter. It's more so for visual thing to see.
So when he first drew it, it was in Z.
Yeah.
And then, but it gives us D.
Well, is that the same Z as what the other stuff?
Yes, it is. It's just switch because Z equals negative L like you
Okay,
said.
well then that makes
And then
sense.
D
Going
equals-
negative.
Yeah.
We're good now.
8 is the frame of reference change halfway through.
Okay, we're better.
Yeah. Who's smart in this?
No, I'm a bad teacher right now, okay? Okay,
Wow,
I am
that's
a bad teacher right now, okay? It is my apologies for it. It's just I wasn't as prepared as I wanted to be for this, honestly.
Josh just keeps on rumbling. I'm like, wait, hold on. I'm barely like in
Yeah.
step 1.
We're all in the same sinking ship. Don't worry.
I just talk a lot, guys. I'm sorry.
It's no worries, okay. Okay, but I'm gonna complete this problem though, okay? I wanna finish this off.
Okay, go ahead and finish this and then we move on.
Yeah.
It's getting kind of late.
Was more so.
Only to 9, bro.
Yeah, it's
Yeah,
9.
we got 4 of the
Oh,
problem.
I'm sorry.
Or if we want to cover 4 of the problems.
Never mind.
Well, I want to cover a different problem for sure.
Okay, but basically, okay. So after you add in your respective half wavelengths, right? Your D1 should come out to be this fine dandy number, and your other one should also be after range.
D1 is just outside, it's 0.7999.
Yes.
Sweet.
But which value did I use?
That's,
D2.
which, wait,
One?
and the other one's 1.0?
It's 1 point, and then the other one is 0.7.
I would say- No.
No, D1 because it's the closest.
Yeah, you would do.
So like, look at the answer.
I would say D2 because D1.
Close position, so it would be D1.
It'll be 1.
I just didn't read the question.
That's probably. Well, but that's the farthest, it was 0.7 lambdas are cut off.
Further than.
Further than would be 1. Think of it as like a scale factor, right?
Yeah.
So because lambda is just some length, okay? If you were to actually input a finite number there, the 0.7 is simply closer, so it's gonna be a better value, I guess. per se.
Could you mark D1 and D2 on that original drawing with 0.7 lambda?
Yeah, let me actually redraw it now. Okay.
Then we put the stuff in the equations and they don't.
Speak up, Joe.
Oh, well, I didn't get the same values for D1 and D2. Both of mine are still less than 0.7 lambda. I'm not sure if I did the values wrong or.
You just,
What's your theta prime?
My theta prime is plus or minus 1.85922. We got the same D1s, but when we added lambda over 2, we got different answers.
did you add lambda maybe? Did you add lambda? Because if it repeats,
It should have been only a half wavelength, or shifted in half.
well, the reason why I was gonna say, if he said it's not getting it at a half wavelength, if it repeats again, why don't just do another?
You can't do that. I have seen problems where you can, because I've seen problems where we have to shift it in 3 times.
That would make the most sense. If it was one wavelength, what is it? Because you had a negative 0.2
Mhm.
and you got a positive 0.79. One.
Oh,
lambda.
wait, no, you know what? Yeah, I think I have to did.
So
Should go twice.
add another lambda,
Yeah,
or add another lambda over 2.
Or lambda over 2 specifically, yes.
Yeah, because that would make
I
the most
made,
sense.
yeah, it would.
Because the other
Crazy.
one was a positive 0.95
Yeah,
and now you're,
because it'd just be a 0.5.
yeah, exactly. So, yeah, you added a full, you
I added a
lambda.
full wavelength to it.
So add lambda instead of lambda over 2.
As many as you want, okay? Because the biggest thing is the goal is to get it out of the restrictive range of what we were given, which is 0.7, right?
Okay.
Once when it's out of that range, you can stop.
Yeah, if I add a full lambda, I get the same values.
We shifted over by lambda over 2 is just simply because,
Stuff repeats at lambda over 2.
yes, it repeats every half a wavelength.
I can do this.
That's the biggest thing. It will repeat at every half wavelength. You can shift over as many times as you need to. In this case, we did shift over to twice.
Okay.
Okay, and then physically on the map, we're basically saying at some length, right? This is our 0.7 lambda. This is just for reference, not actual scale. Okay, and we're saying D1 is just D1 right there, and then we're saying D2 is like way over here. Okay.
Yeah.
Because.
That's whole-
Same every time. It repeats it, and we're doing it because the first values were either,
Yeah.
no, it's on the wrong side of this, our load.
Cool.
Or
Stuff
it's
like
too
that.
close.
And so you would use D1, like you
So
said.
we use D1. So now for all our future math right now, we're using D1, okay? In reference to this problem is D1, okay? Again, it will not always be D1. It may be some other distance, okay? Just keep that in mind. From here, you have to find your other components now. Your BS, your acceptance, your ZS, and then your LS, right? Those are the long equations I hate doing a lot. It's just okay, LS is a little extra. No, it's not. In this case, it's not.
Oh, okay.
Because the length is essentially the length of the actual stub. How far out you're putting your mesh. Okay, the distance is how far away from the load.
Yes.
The length is how far or how much transmission line you're gonna actually add to that load. Because the distance, we're just saying it's on the transmission line still, right? Length is just basically like how much of a transmission line.
What do you mean? Like how much you're gonna have to like in parallel when you?
Not
put it in?
parallel. The distance is just in parallel.
Right.
Yeah, the length is literally how long that transmission is gonna be.
It's like from the point to actually stub, like how much transmission line you gotta add.
Yes,
Oh, you mean length of the, okay,
Oh.
I got you now.
yeah,
Yeah,
that's
I
what
got
those
you.
values are at the end of the day.
Yeah,
That's
yeah,
what those values are.
okay.
People forget that the length matters because the
Yeah.
problem is even asking you to like, hey, find a distance greater than 0.7 lambda and the length
Was it the length?
in lambda length. Yes,
Reading sure as hell.
reading is definitely helpful. Okay. Those dang equations though, very annoying, honestly.
Yeah, because you also have to do like the Z and stuff, right, for the length.
It doesn't even really tell us the actual equation. Do you
Um,
have the equation for L's?
yeah.
Francis, I'm sorry to interrupt.
By all means.
Would you be opposed to just doing this problem, calling it at 8, and then tomorrow do another problem, and then so on? That way we don't have like
It's
two
up to you.
full video, 2-hour video, of, like, bunch of chit chat in between. Up to you. And
So what's
you-
that?
you can be
I'm gonna have to
prepared.
disagree with that.
I was about to say, it looks like we're only gonna get to 2, maybe 3, bro.
I'm gonna have to disagree, but I can follow up. Because I did schedule my time to be here until 9. I can work something out to record myself just kind of talking again, more prepared and just kind of post that too. So
Right, which is.
Yeah. I guess I'll call this more of like a open chat, then I'll record myself actually working out more different problems and posting that too.
Let's get through this first, we can find that.
Yeah. Okay. I really don't want to derive the BS equation right now,
I can literally give it to you right now if you want it.
by all means.
Yeah.
I'll just bring my laptop so you kind of get kind of a nice read today.
Yeah, that works. Because I did one day, I typed it into my calculator already, so that's the one I was looking for.
There you go.
We can work problems tomorrow.
So just doing it at the admittance way, so not
That's what
this is the
works.
new.
No, it works, okay, and I'm almost getting to that point.
Like, yeah, I don't know what she's talking about. But-
No, I know, this is it right here.
Well, yeah, that, but like, technically, this is using the admittance part, because if you,
It's literally right here. This is
Yeah.
the last part where you just change your math a little bit. That's
yeah, I
it.
was about to say, because they go back to impedances though.
Yes, exactly. No, that's the whole reason why I'm saying if you manipulate your math here.
Oh, got it, okay.
Yeah, that's the part I was trying to just tell it to wait off a little bit, so,
Gotcha.
yeah.
You get it up?
And then your DS, no, we already got DS
Yeah,
actually.
what is it? Then this is, S.
Yeah, that's
Z.
looking enough, yeah. Well, that's not the one we're using for this one though.
What do you mean? It's not the one?
She
you-
is
Oh,
done.
one that you're gonna, so I got you.
Okay.
Absolutely.
Okay,
Sorry, you get.
so Leslie, to address your point, okay. The thing you're caught up on right now is understandable, right? We normalize load, okay? That's all we're doing is saying Z naught over ZL, right? Whenever you're trying to find your impedance of your submatch, like the actual shunt you're gonna be putting in there, right?
Mhm.
It comes back down to, okay, we're trying to find the real of it, right? The real of it, because we're not,
In admittance?
let me rephrase that. Let me
What
rephrase
page
that.
are you at?
This is the 6th edition, 103.
103.
Yes. Basically, the biggest thing right here, okay, is whatever BS value you're given, right? Because the sign matters a lot on here. The sign matters there the most, okay? And in this case, it's actually right there. If you don't normalize it, okay, you just kind of jump where that line of math is right there. Because you've seen this example, right? I'm guessing, right? The one inside the book.
Yeah,
You see the first few lines of math, that YS and stuff.
right.
You just kind of jump to the very last section of it.
if you weren't to normalize
Normalize,
it.
yes.
Okay, so that BS is normalizing it or not normalizing it. That distance to the stud is that equation.
Mhm.
Period.
Yes,
Yeah, the only equation that matters if it's normalized or not would be band in this.
yes, that's the only real thing, but even then, you're gonna get the same value.
Yeah,
Yeah.
You can do, I've done the math both ways, it's gonna get you the same value, as long as you don't make mistakes or do any weird stuff there, okay?
if you were to like normalize it.
No, that's what I mean, like towards the, if you start your problem normalizing it, you have to unnormalize it again towards the end.
Yes.
That's what I'm
Yes.
going with.
Gotcha.
So that's where I was like, are you going towards the end, since you didn't start normalize it, are you going to normalize it then? That's where I'm rolling, like I have different questions for the approaches that he's taking.
Gotcha.
I like using the tangent because all this equation comes from is whenever you actually find ZS, right? So this is normally the equation you use just for finding ZS, right? Where ZS is equal to 2 pi over lambda is equal to type 2 pi over lambda tangent your let me find the actual equation I'm referring to. All it is, because okay, so funny thing is a lot of the math I'm using right now is basically rearranged equations from chapter 2.
Right.
Well, what you originally learned, because the equation I'm thinking of right now
Mhm.
is back to this one right here. So basically,
What page?
84 in the book.
84.
Yes. Yeah, but you'll be fine. Because talking it out is the biggest thing, right?
Yeah.
Talking it out.
Do all this and not make mistakes is gonna be.
Why are you finding Z in?
Oh, that's the end open circuit because the stub can be open or closed.
Yes.
Say to find that?
Oh, let me says short circuit stuff.
No, I.
Oh, short circuit.
Oh.
Mm,
I have to remember that.
Yeah, reading is gonna be very important.
Right.
Reading is gonna be very important indeed. And again, all this equation comes from
Mhm.
right here. This negative J or whatever value you get there really tells you
Short
if it's
circuit
an
up top?
open or a short circuit.
Short circuits up top.
Yes.
Got it.
And depending on what that value is, you either use the length found in either of these equations, because all I did was just literally rearrange it.
That's so much simpler than I was
For you.
thinking. That's great.
This is a derivation we figured out way back when. But basically, all I did, right? All I did, I rearranged the short circuit equation to find length instead.
We're using tangent and cotangent on sine and cosine design.
Okay.
That's
Now,
awesome. That length,
Mhm.
is that now what you use on that L? The length S, is that what which you use on the Z short circuit and Z open circuit?
Yes.
Okay, cool.
It just depends what the ZS value is. Okay.
So if it were to be, if J was positive, then you would have used the
Open.
open circle.
You could just say it.
Yeah.
Yeah,
Or ZS is negative.
but I say I think I was gonna double back on that.
So
Maybe for
I
corresponding
was
competing-
trying to solve for the link and I actually got
Shift it in again.
shifted again.
Yeah.
I would,
By half wavelength again, because it is gonna get you. Wait for the ZS value, you mean, or
for the L.
LS?
Yeah.
So then
L.
shift it again.
So I'm doing.
Yeah, the same rules apply.
The X.
Because that's what I do here too. I was gonna get to that. Yeah, no worries. Yeah. So okay, your LS value. It's okay if it's negative. Okay.
Is that
It's
Z,
okay if it's negative.
is that ZS over JZS
Uh,
in the LS equation?
No.
Z naught over JBS, negative JBS.
No,
Is
it's
it?
LS equation.
ZSORJ.
Got it.
Yeah.
Francis, I'm so sorry, just to recap,
Mhm.
because I just explained something to her and I don't want to be wrong.
Yeah.
The reason ZS is negative and we are using the short circuit because we didn't normalize it, right?
We normalize it, so this is what the value would be.
Right,
Right.
okay, that's why we're using the short circuit,
Yes.
basically, okay.
And your LS, okay, well, what's your name, actually? I don't know you. Gabby? Francis. Very nice to meet you too. One quick note before we discuss a little more, the LS value can be negative again, okay? Same principle applies though. It's simply just not on a section we're allowed to use, just shift it, or going in the wrong direction, I should say. Just shift it over by however many half wavelengths you would need to. Because in this case, we do shift it over one last time. Okay. So then the final value for LS should be and this was the acceptable answer. Your D1 is acceptable answer there, and then oops.
Yeah.
Yeah, so the final answers you would be putting down would be your LS and
D1.
D1. Because the final question was just asking you find closest position greater than that. So the distance from your load and the length of that stuff,
Yeah.
whatever it may be.
Can you go back down a couple lines or up?
Yeah, but it's so basically just to recap, find your gamma. Okay, for this specific problem, we're locked out of a region. That doesn't matter though until towards the very end. You're locked out of a region. You're given a single load, say impedance match. Find your gamma. Find your magnitude. I recommend polar just because you can look at your theta in the exponent of it.
Yes.
That's your theta r. Okay.
And your magnitude.
And your magnitude is also in there as well. Theta prime is just a quick math. If you did it in polar form, just theta prime, theta r minus literally 2 pi over lambda.
Just 2 beta D, I think.
Basically, as just 2 beta d.
Oh,
really
right,
right
yeah.
there. Yeah. Okay. Then you have everything you need already, basically. That's literally like 3 lines of math. You're set now. You're fine. No, this is what is the more you look at this, more it's just like, damn, this shit's
No.
God.
then you find your DS, okay? Because you have your prime, your theta prime, and your theta r. You get 2 values there, okay? Because we have 2 values of theta prime, right? Check both. You find 2 values of your distance. Shift it in if you have to, depending on what the question's asking for, right? Once you find the correct distance, you work with it. Yes. Then you find that freaking what was it called again? The BS
Susceptance?
susceptance. Yes.
Acceptance.
Yes. I hate this equation. This is the only one really.
What'd you say?
I hate it a lot. It sucks. I would recommend pre-programming it if you can. Or just put on your formula sheet. Yeah. You get a value there. It's one value, maybe positive or negative. Doesn't really matter. It matters though whenever you actually try and do this equation right here. Okay. Because the actual math, this stays the same basically. The value you spit out there will make you check your knowledge if it's an open or if it's going to be a short, basically an inductor or a capacitor.
And short would be, I'm sorry, if it's negative, it would be a short circuit. Correct? Because short circuit,
Negative where?
sorry, if the ZS is negative, you'd be using the short circuit.
Yes.
Positive, use the open circuit. Got it. And the way I'm thinking about that is like an inductor capacitor.
That's exactly what it is. That's
Okay, because I was
exactly
gonna
what
say,
it
we
is.
saw it in the book, we found a capacitor and inductor.
Mhm.
And when it was negative, found an.
Well, I do have a question about that because your short circuited line can act like both.
It can.
Wait. I have that wrong. I have that wrong.
Oh,
Or at least I thought I had that wrong.
did I correct it in my? Because I think I already corrected what we said in my head.
A positive ZS gives us an inductor.
Yeah,
So a positive ZS would give you the short.
the short circuit.
Got it. Got it.
It's the opposite wherever yeah, I'm gonna retract that statement. To answer your question though,
Do one win. Which one he wants us to do.
basically, it just dictates which one, because he might send a problem, open or short circuit, then you already know which way to use. But you yourself have to also identify, just based off the value, which one you would actually use. Because I have seen problems where he'll say, give me a short circuit and an open circuit. And that basically just means going back to your data prime values and just choosing both instead.
You what?
But that's a different problem though. I'm not gonna bring it up anymore. Basically, all I'm saying is, in case he tells you find a short or an open circuit, you have to know how to manipulate that. Because all it's saying is do your math still right. Pick the values though that will get you the open circuit or the short circuit stuff. So figuring out, again, you want a capacitor or do you want a inductor? From there, you already know the line of math you have to use. Just be careful about that. I'm gonna clean this up a lot. Yeah, I'm gonna clean this up a lot. Want to do a physics problem?
Yes, please.
Physics. Conducting wire. It's fun. It's amazing. I like it a lot. Sure.
This is the one. Yeah. Got it. So, yeah.
Okay. Physics time. Conducting wires formed into square loop. So guess what? I will physically draw the loop, okay? Because goddamn, I'll be damned if it's because I don't know how to do a perimeter, okay? Damned if I do, damned if I don't, okay? Because he might toss you a square or a circle or a triangle, okay? He will do that.
You won't give like a super random shape, right?
No, it'll be basic. Just actually know the formulas though, okay? Because
Okay.
I have blanked out for like 2 minutes. I'm just like, how do I find perimeter again? Okay, know your shapes. Just know your shapes, please.
Yep, so.
Just know your shapes. I've seen these three for sure. I haven't seen, well, I've seen square and a rectangle. I've seen both. Okay, so just be careful about that. Just wanted to throw it out. The internal resistance of a loop is 3 ohms. The wire loop is placed on the XY plane, so that matters a lot. The XY plane. In free space, center of the loop at the origin. Okay, so you can actually draw out now
Oh, I hate drawing.
how the problem is actually shaped now. Okay, so we're saying some length of sorts at the origin, or the center of the shape is where the origin at, right? And we're saying it's a square. So this is what it is. And this is your XY plane, okay? So you're saying on your XY plane lies this shape with the center is at the origin as well. Area is bounded by a loop of 1 meter squared. So we're saying area is equal to 1 meter squared. Guess what? It's a square. So now we know what the lengths are. If we didn't know, if it was a different shape, this is where those just basic geometry stuff, like area is equal to what for triangle.
What happens?
Exactly.
Yeah.
Yeah.
I remember that.
Yeah,
But
but
we put a triangle or a square?
triangle.
Oh, okay.
Right, yeah. Yeah, basically, so guess what? The area per square is just literally side times side, right? So guess what?
Yeah.
One side length is equal to 1 meter, right? If it was a triangle, it'd be a little bit different, right? If it was a circle, again, it would be. I don't remember the area of freaking circle. I'm sad.
Is it 435?
That is vol.
Of a sphere.
Pi or square.
Is it just pi or square?
It's just pi or square.
I guess I don't know, man. Okay, enough.
Pi or squared.
Enough of that. Okay. It's sides oriented parallel to the x and y. That's the big thing right there. Yes, to x and y. Okay. Magnetic field. So we're gonna go ahead and write it out because I like writing it out. The magnetic field is this grand old equation. Looks scary. It's not. Trust me.
Oh, looks like it.
No, it's not. You just gotta manipulate it a little bit. Okay, don't worry about the units so much. Don't get hung up on that. Units, where are they? Who cares? Yeah, I know
That's
it's watch
so-
cares. I know it's watch cares. I work in engineering units now, okay?
That's fair.
The biggest thing of this equation I'm concerned about is really this right here. Now I'll explain in a bit. Okay, I'm mostly concerned about that.
You're mostly concerned about the cosine.
Yeah, the cosine value.
That also gives us our frequency, right?
Hmm.
Our angular frequency.
It's specifically that, yes.
Wow.
So now all I want to find is current and electric field, okay? Current trips people up a lot because it's pretty obvious when it comes to a symmetrical shape. If it's not symmetrical, you're kind of screwed a little bit. You have to do some actual math. But which section do you think is actually easier to solve first?
Which section?
A or B? Because you technically don't really need one or the other to solve either of
Let's
these
go.
parts.
With B, because it's less points.
Yes.
Wasn't it H equals mu B or
B equals mu H.
B equals mu H?
So the mu's would cancel out when you're trying to solve for magnetic force.
You already solved it basically. For
you
it is 0, yeah.
I didn't say it was 0.
Well,
I said
it-
the mu's would cancel out.
They cancel out though.
Oh.
The math here, I'll go and show you. I'll go and show you real quick. Okay. Basically, it is no, that's yeah, no, it's crazy how that works, right? This is such a trick question and I hate it. This is such a trick question. I hate it, dude. I hate it because okay, so all I did was just basically go ahead and convert it into phasor notation, right? So all I just is say, hey, this stuff doesn't exist anymore inside the phasor domain, right? Mhm.
So the cosine T thing don't matter.
Exactly.
Okay.
Okay. Don't worry about that because this is still just basic, like, just going into one domain to another, right?
Okay, cool. So would you recommend on these type of problems going into phasor domain?
Typically, yes.
Typically.
Typically, yes.
It could be my shoe. It's definitely my home shoe.
Maybe.
I hosed it off. Okay. Oh,
Okay. What is not EMF? Actually, yeah. What is the
yeah, electric motor force.
yeah. Yeah, I'm crazy. What is this equation though? Whoops. Well, this goes back to your physics stuff. Okay, so give me any. It's not static.
Right.
Say it's not static because it's time varying.
Originally, it is, yes.
Yeah, because that's pretty.
But we have to treat it like a.
Saying that E, equals. That's stupid, partial derivative over partial T, B. Are you talking about that?
You're thinking in right terms. That's not the equation I'm looking for, though.
But you're talking about Faraday, right?
Yeah, because okay, the goal right now is you either want to find the current in the loop or the electric field intensity in the region, right? One involves the area of it. The other one is just literally finding the current traveling in the perimeter of it. The key, yeah. So basically, we either are trying to find first the current traveling in the square or the field that's getting
Inside the square.
yes. So right now we're trying to find the electric field intensity first, okay? That's VMF. Is that oh you're looking at that one.
Is it not that?
That's in the closed loop. Well, can I see that a little closer? I'm
That's what Faraday is in the book.
No. No,
no.
no, no, got it. Okay.
But still keep that equation up because that is useful for
Wait.
No, yeah, it should be that.
Wait, what?
Look, oh, this one.
During the integral form.
That's in the end.
Why are we not doing integral form? I thought we wanted to know the inside.
There's a default here. Okay, let me just no because you're already serious. Okay, so no, that's the thing. Okay, that's specifically B. Okay, Okay, but that's not the equation though. That's not the equation I'm looking for though.
Are you looking for the?
I'm looking for-
electric field version?
Basically,
Okay, so you're looking for the left half, there it is.
I'm looking for that del stuff.
Oh,
Del cross.
That's different.
Yeah.
Okay,
Yeah,
so.
we're gonna use both forms though.
This would just be.
Yeah, because we're using the closed integral form for this one right here versus the not the differential, the partial
Okay.
derivative one.
Zach, can you talk to him about what Wash told you today, the time harmonic thing or whatever?
That's what I'm thinking of. This is
Well,
the
yeah, so-
main, the time harmonic.
Yeah, so I have this problem, because it was on mine. This is the one from last semester.
Yes, so you're
Uh,
correct about that.
I was having a hard time solving B,
Hmm.
and so I went and talked to Tawashi today,
Yeah.
and he did what this is. He didn't talk to us about this formula yet, though. But when I looked in the book, it's like a time harmonic form of Ampere's law,
Mhm.
and
Yes.
yeah, I mean, I don't really know like how he got it or like what it means, but he did talk to me about this.
Okay,
This paper.
I don't like
Yeah,
that,
I
but
figured, yeah.
yeah, I don't like that, but
Because how I was trying to do it when I first saw it, because I only knew the differential form of Faraday's law.
Yeah.
And so I took like the del of, I was trying to find, because del of basically the curl of E equals the negative derivative.
it's specifically the curl
of E.
we are looking at the most, because this specifically is your curl.
Right. But yeah, the curl of the electric field is equal to that negative time derivative of your B.
Mhm.
And so I was trying to do that and then, break down the components of what the curl equals into the components of the electric field. And then I got stuck. And then I went to talk to watch it. He was like, oh, well, just use this equation and it equals 0.
That's where we're getting at right now. Yeah, no, that's exactly what we're getting at right now.
Bar magnitude,
There's a few mu H.
It's not mu H.
No.
No, okay, that's just me in my like phasor notation.
Okay, I
Yeah,
was
it's
just
just a weird phasor.
Wait,
Yeah, because you can no, because I've seen it like this, where it's like people connect it, or it's just like the Bolden of it, right? It just really depends on who you ask about it. A physicist will probably give you the bold version of it. We like usually see it like this, right? It doesn't really matter though at the end of the day, as long as you read the notation of it right. But you're going exactly where I was gonna go. Where basically this section right here, specifically the curl across the field, is just equal to. I'm gonna write out the actual notation of what this means first, right? Okay, because all this is just saying you're doing partial derivatives. Am I right there, right? Yeah.
So yeah, what he bring down?
Yeah, no, yeah, because I'm trying to remember how the actual derivation is, because it's like am I, can I see? Because I don't remember the next two lines.
The unit vector should be on top.
That's what I was thinking. It's the unit vector. That's where I was screwing up. Okay.
Yeah, so this theoretically.
And then it's the partials.
The partials afterwards. Yeah, no, yeah. I forgot about that. My bad. Because this right here is what I like enjoyed a lot doing it. But this actually goes back to more of a math thing, right? So then all we're saying is we're gonna do a different of your x. There you go. Okay. Okay, we're going back to math now, okay?
Okay.
Del of a cross product of any vector per se is just the determinant of this, right? Or basically your unit vector, your partial derivatives, and then your components of your x, y, and z, right?
Okay.
All we're doing is saying, hey, multiply this entire thing by a factor of JWT, right? So the actual math we're doing in this equation is actually just a 3x3 determinant. You can actually plug in values here if you want. I'm going to show it to you numerically first and then show you how it cancels out. Okay. Because that I actually do have down because this math was very fun for me back then. Okay, so what you should get out if you actually follow just, your basic 3x3 determinate rules, right? Where the cross product of your del is just equal to your x component of u of h z dy, your y component of your y component. No, all this is basically following your basic 3x3 determinant rules, right? Because I did this right here a lot during the exams and such, right? It just to show the math because I was very paranoid of Dr. Tawacha, but it also made me comfortable in showing this trick right here because students forget what this specifically means. Students forget how to do a cross product. Just know the cross product. This is what it is. Yeah, because this right here, all it is just your partial derivatives of your x, y, and z, right? This is technically broken up into 3 components of your x, y, and z of it. The cross is just basically saying your unit vector, like with respect to it. That's all we're saying here, okay? So now we're gonna actually just by inspection do derivatives. And it's gonna be real quick, obvious. Okay, so the z component with respect to y, what's the derivative of that?
0.
Cool. Your h component with respect to z,
So 0.
and then that's literally it cancels out the freaking 0, man. Okay. So then we're saying your phasor though, you have to write this final step or else he will not count it. Your phasor is 0, but your time domain 0. I like and I hate this problem because it makes you really think of just a little bit about how to solve a problem. And then the next part is actually really easy. Next part is super, super easy. Because all we're saying is your magnetic field, right? Plug and play. This is where that math comes into play. Because from here, the actual, yeah, I just write the actual close space. So, okay, we're gonna set the balance first. Okay, that's what I want to. So I'm saying this is a 1 by 1 square. The origin is at its center. How do I set up my bounds?
Question. You're saying the electric fields now go to 0.
We just showed it numerically.
We found the curl of the magnetic and field intensity.
Mhm.
And just that equals E. I just want to clarify.
Yeah, no, yeah. The original line we're trying to prove is this right here.
Yes.
Yeah.
But, okay, got
The scale, okay, but there was nothing to multiply by this 1 over j omega t.
Yes, I got you.
So it just cancels out too.
J omega t came from, we got into phasor, for I assume, right? But if I remember correctly, when I think of phasor, I think of going to like inductors and capacitors.
Mhm.
And that to me looks like a capacitor type thing. Why did you choose that one instead of J omega T? I'm just here. You get what I'm asking, right?
Yeah. I get what you're asking.
Never mind, it's literally on the book. Okay.
But I say, I was about to say, I think the book explains it better to me there. Isn't it supposed to be negative? Did I forget to carry that?
H.
Where?
So for H, when you're multiplying it, or it becomes, yeah, I think it's supposed to be negative. 1 over negative, J omega. times- Yeah.
Well, it's just negative 1 over J omega U. Way over. I'm sorry. No.
But I said, I don't recall mu being,
The-
well, no, there is a mu depending on which one you're looking at. Maybe.
So what?
It might be negative, might not be. I will double check.
It's not negative.
It's not negative?
It's not negative.
Quick,
I'm just looking at it.
what happened to the cosine? Like real quick. Sorry, I know it's all the way back to the beginning.
No. The cosine doesn't matter for phasor.
But we moved to the phaser,
It's times even by 0.
like on that top formula, how is that phaser?
This
There's
right here?
no like. Phasers.
We do a quick
You're right.
conversion over to the phasor domain, right? So this is technically just that,
I know that part goes away
Mhm.
because you can just,
Yeah.
because
right here.
time doesn't matter in phasor because you reduce variable.
yes,
But then how does that other formula for the magnetic intensity or
this
the
right here,
intensity?
this right here.
No, the H one, the other
H
H
one?
phaser.
The other
We
H
originally have it.
Because you know how it's, when you're in the time domain,
Uh-huh.
if there's like a phase offset,
Uh-huh.
that would be your E to the J phase offset.
Right, but.
Because there is no phase offset. It's E to the 0. And then.
Okay,
so
yeah.
that's just-
Oh, I forgot to explain that. My bad.
Yeah.
Yeah, my bad.
Thanks,
That
Zach.
no, that's why I say I care about that the most because it's really omega t plus whatever phase offset, right? So it could have been like a pi over 2 or whatever omega value or value could have been there.
Yeah.
That's just 0 in our case, right?
Yep.
So this just goes in phasor domain, just the actual values we were given.
Okay.
I forgot to explain that. But back to our bounds.
If it would have been something, what would that have done?
Just the E.
Just added some value to it.
I didn't.
Yeah.
See, got it. Yeah.
That's
okay.
not confusing.
We're good. we're
Yeah,
good,
okay,
got it.
back to this, right? So I need help setting up my bounds right now, okay? How do I set up my bounds, my integral for this, right?
What? I'm gonna say 0 to 1. Okay, doesn't like that answer.
Negative 0.5 to 0.5.
There you go.
Then.
Oh, the magnitude is 1. Yeah, okay. That makes sense. The entire cycling. We're both dumb.
At least we found that out.
There you go. And then what's inside here? Because we're saying it's this B value. What is B and how do I actually like work with it?
Oh, B is just the H value times mu, but the mu's will cancel out.
Exactly. That's why I wrote it here still because it's annoying. Well, not there specifically, but up here. It's right there. So whenever mu, but the mu's cancel out. It's crazy how he sets up the problems.
And the B,
Wait, I'm sorry.
isn't it mu of like the entire mu, not just mu naught? Like B equals mu, right?
It is. mu.
Well, it depends on what the problem asks. If it said free space, then it would.
It is. We are in free space. We are in free space.
Oh, we on this free?
Yes,
Okay.
we are in free
Okay.
space.
Space free, yeah.
It will tell you directly. He will tell you always if it is free space or if there is some weird mu value there.
And we're doing it a double derivative because we're in a surface integral, correct?
Right.
Yes.
Okay. Did you forget, wait, what about the differential up in the front, the derivative?
Negative D dt.
Does that go away or is that still there?
I mean, I'm gonna include it right now,
Okay.
but how would I
Steps, please.
include that though? What does that mean specifically?
I mean, it would only affect cosine.
Mm-hmm.
Is that what?
What direction is that?
What direction?
Or what unit vector I would be putting here? Because this is going back to like calculus 2 stuff right now, basically, right? Because we're in a closed loop right now.
Okay.
We're saying we want to find the area of this section right here with respect to an X domain and a Y domain. What unit vector would I put there to go ahead?
It would be Z.
It would be Z.
Okay.
Because we're in the XY plane, we're trying to find exactly.
So if it was like X Z plane, would be the Y,
Mhm.
or if it was the Y Z plane, be the X.
Yes.
It's basically, you got 3 numbers or 3 letters, whichever
Yeah.
one's not there.
With the direction of the surface, basically.
Basically, yeah. It's just weird stuff that he doesn't cover, but you still expect to remember
Did that
it because you were
confusing?
taught it.
Yeah.
Yeah, I get it. Okay. Yeah, so right now, okay, the problem tells us we're in the XY.
XY, please.
Yes, our wire is on the XY, okay? We
There's one.
are saying, okay, there is some electric field we're trying to find here in this area, right? What direction would that actually be then?
So we're in an XY plane.
We are on, the wire's on XY plane.
Mhm.
What direction would the field be emitted?
You.
Exactly.
Okay, so if our wire was on the XZ domain,
Yeah.
then we would assume that it is going in the Y direction, or magnetic, no, our electric magnetic.
Say magnetic, right?
EMF either way, yeah.
Okay,
B EMS.
Yes.
but okay, so now my question is, how would you determine if it's negative or positive?
The math will actually tell you.
Wait, what?
Gabby, you get that?
What do you mean by, okay, I see what you're talking about.
Hmm?
We will find out, Josh.
No, the actual math is gonna, it's gonna tell you, okay, trust me. Okay,
Well,
Well, do the math.
I guess I should ask. When you're putting in that direction of the unit vector, do you just assume it's positive at the beginning?
Because
Okay,
we're
cool.
doing the
That's all.
right hand.
Yeah.
That's, all I know is the right hand is that, right, but with the X. So that's why I'm asking, like, what about if it was on the X Z plane? And so now we know that it's on the Y, but then is it this way or is it this way? You know what I'm saying? Like,
yeah, and it's, the math will tell us, okay?
Okay.
Why? Because guess what? This is still a dot product. You guys remember how to do your dots?
Yeah,
They're pretty easy.
well, the first one would be 0, the second one would just be 0.35, right? Negative 0.35?
You got it. That's crazy how a dot times itself is just one. Whoa, a dot times not itself, basically, like say x times x dot z does not get you y. It's 0 because reasons. I can't explain that to you right now because that's like a whole actual math concept we taught way back when.
Okay.
Yes.
Chapter 3 in the book.
that X times X.
Let me look up a dot product.
Y times Y equals Z times Z equals 1.
Yeah.
Well, that, is that where you're,
Yeah,
Okay, okay.
dotting
And
two
then-
unit vectors, if they're the same,
it's 1.
it's 1.
Yeah.
Because a dot product shows like some similarity between
Right, right, right.
unit vectors get going.
Yeah, and it's on chapter 3.
Yeah.
Okay.
Yes.
Yeah.
But I actually write down what the dots are real quick. Just give me a second to find an actual link for it. But this is weird how all this comes back together. I hate it a lot.
Bro, this class is literally every.
Yeah, no, there's a reason why people struggle. Thanks, that coding.
Well,
I hear that.
Chapter 3.
Yes.
Yeah.
Class, yeah.
Okay, so we have that there now. So, because I'm actually walking through how I, well, yeah, freaking Josh already told it actually. Josh already said the answer, man. Way too early.
I'm
Fun.
You're being Alex.
Well, I guess I should ask. Twacha always does the derivative at the end.
Hmm?
Does it really matter?
No, it does, because I realized I misspoke when I said that this doesn't cancel out the derivative. You do the derivative at the end though.
Okay.
Because we're not gonna just shove this in there. You can, it's not friendly though. Most students don't know how to just take in a derivative into your integral. It's not standard stuff you get taught. It's a very weird process to do not recommend it. If you know how to do it, great. Flex that math.
Also, it's not just as simple as just doing the derivative before doing the integral.
No.
Okay,
No.
that's good to know.
Basically, I guess my question is, did you forget to put the DDT at the front of those intervals?
Yeah, I'm being lazy and about rewriting it, okay? So basically,
No, DD.
Well, that's.
It's like negative
this is just to show more visibly like what is going on here, okay? Because all we're saying is this, right? 0.5 to negative 0.5. Doing the actual integral, all you're doing is just taking out 35, 120 again, doing that whole math, it's gonna cancel itself out. Okay. The biggest thing is though, you're left with some weird W at the end, right? It's not cosine sine.
So wait, we have now,
Did our double integral already? Okay, this is it. This is what the double integral is, but we still have to multiply it by that.
What did it go from cosine to sine back to cosine?
It will go back to cosine.
Oh, okay, sorry.
wait,
No, it's not. No. It's not.
because we're just integrating with respect to X and Y, and then we
Yeah.
just go to 1.
And then
Oh, because T's not part of that.
yes.
Oh, okay.
That's why I write that final form here because like, you know, this is what it would be at the end of the day, right?
Okay, got you. So if we were to integrate the X and Ys, it would just be literally an X times a Y, and it would go from negative
To positive.
to positive, which
And then-
is just if you make them together, if you want.
Yeah, and then you do the derivative of that final value, right?
Got it.
Which is just this one I hate a lot because that people trip up on the actual final value of what the derivative could be. So just be careful about that. Yes, I will. And all I did with this W on the outside just literally multiplied it. It doesn't that one doesn't even matter too much. Just be careful about it, okay? And this is what he deemed was the final answer. And this was also correct too.
Okay.
But basically, okay, this part right here. Okay. Depending the shape. This is where people get tripped up. Depending the shape.
Depending on the shape.
Depending the shape, okay?
Depending the
If
shape.
we got lucky, it was a square. We could easily set our bounds, right?
Right, why did we set our bounds to 0.5 and negative 0?
It's negative 0.5, 2.5.
What?
Negative point, so
Negative 0.5.
no, it's negative 0.5, okay? Because we're saying the origin is at its center of the shape, right? So, yes, okay? Now, imagine it wasn't.
Okay,
All you're doing is just shifting the bounds. And with respect to a square, it's easier to see and do it, okay? Because we're just saying, okay, if the origin was at the bottom of the corner, and we're saying 0, 0 is the origin, and you're traveling along the right-hand side, this would be 0 to 1. We're traveling on going up, which is whatever direction it is, it'd be 0 to 1 there too. It just depends on where the origin is specifically.
So this origin was here. The y would still be from the negative 0.5 to 0.5. But the x would be from 0 to 1, correct?
Or negative 1 to 0, depending on the, because again, the origin, it's specifically the origin. Right?
So, but however, can. So, but although. Where it is, it wouldn't matter, right? Because we're already given the value of the area.
Yeah.
And so, because once you integrate over that surface, you know, you're gonna have the area of the surface.
Mhm.
So you can just multiply your final integral. Or whatever your interval gives you by that A, right?
There's another way around it. Because it depends if you see the math, right?
Yeah.
There's plenty of ways to figure out how to do
This actually.
this. Is just a double integral at the end of the day, right?
Yes.
However you want to tackle that, it's up to you. Okay, we just did the actual math. We just did the actual math because this math wasn't too bad. The hardest part is probably remembering, hey, this is still a dot product.
We still have the first one.
Do not forget that. The first part is done right.
Yeah,
What?
Yeah, no, we found
Electric field, 0.
electric field is equal to 0.
No.
Oh,
The first part is the current.
Well, okay, again, this is what I meant when I said like every problem you give does not mean we'll solve it in order of the
Yes,
parts you're asked.
Okay, I got you.
Okay,
I was
we
just
solved
asking
part
you
B
how-
first. Yeah, we solved part B first. That's the current. We just found the current.
Huh?
no, we don't need.
No, B was this one right here.
We found the V at V and F.
Yeah.
Found the voltage.
Yeah, VMF is this.
Wait, how is there current? on the-
Oh wait, no, hold on. I forgot to explain that part. Yeah, my bad. Okay. Current is not 0. Current is not 0. Electric field 0
Yeah.
because we're canceling it out.
How is there current without electric field? You're talking about displacement current?
That's technically what he's asking for, right? That's why he specifically labeled it as VEMF, right?
Keep going up.
Okay, no, okay. This is one of the things a little bit hard for me to explain. Okay, just because your electric field's canceled does not mean there is still current present, because we're not saying current getting emitted, current traveling through the loop.
Hmm. Okay.
Typically, that value is not 0. Typically, it's not. Only time it is 0 is if like. What is a good example?
Because total current is conductance or conductive current and the plus the displacement current. This could be one or the other depending on if there's electric field or not. But if there's not an electric field, there can't be a conductive current, right?
That's yes. Okay, yeah.
Okay, but there
Again.
can still be a displacement current.
Yes. Okay. I hated this part of freaking class, dude. Okay. Basically, to reiterate what was just said, okay, just because the electric field is determined to be 0 does not mean there is still some sort of current traveling through the loop, okay? It is specifically conductive current plus displacement, okay? Your conductive basically just means there's current in your loop, right? Displacement is essentially not where God, I hate I don't-
Displacement would be with time.
Yes, that's
Yeah.
what I'm thinking of. Yes. Yes, with respect to time
Yes.
is something moving there, okay?
Right. And because it's not,
Conductive is basically the intrinsic current going in it, right? Or
Yeah.
traveling through it. Okay, this is, I hate how much of this is coming back.
What I said, was that still correct or is that wrong?
No, it is,
Okay.
yeah. That's why I know, that's why I wanted to like iterate again, okay?
Okay, yeah.
But yeah, so again, the current problem, like wherever you're given, the biggest thing is know your shape, understand it, understand how to manipulate a grid, right? And then from there, it's really, okay, do you understand the behavior between going from magnetic to your electric to your magnetic flux current, electric field, and then converting any of it into phasor and then working with the time varying, not the time varying, yeah. Time varying Maxwell equations, both the closed forms and the open forms, okay? Knowing any of that, he can toss it to you, okay?
Closed is the
The,
derivative forms or?
basically, yeah.
Yeah, okay.
Yeah, and the book explains it. It actually like it has like a side by side, like, hey, this is one relationship,
Yeah.
here's the other. The book actually, I like the book for this chapter. I would recommend it. The biggest thing is don't forget, right? He gives you one over mu naught. Okay, mu naught is equal to free space. We're in free space. So whenever we actually go through and do the math, the mu's cancel out specifically here.
Do me a favor and write V equals mu not H, because it's,
This is expected to be trivial for him, that's why.
yeah, well, it is, but like, just to write.
No, I forgot to write it. You're right, though. It's,
You're not, it is like, well, it's what's expected, but yeah.
he will tell you an actual mu value, or it will be worded free space.
The word free space. It's in the second one.
So when it says free space,
Mu knots are
Blind?
fair game to get canceled at some point, if they do.
right, oh, I was just gonna say,
In free
free space is mu naught and epsilon naught.
Yeah,
But isn't it like typically mu naught is, or equal to, like, in any material, it's equal to mu naught?
it's factor of mu naught.
That's schematic, right?
Oh,
The factor of mu naught, because that's another problem. He will toss at you sometimes.
Okay.
Where if you're not careful, he'll tell you, well, okay, he didn't cover capacitors and battery conditions and none of that stuff, right?
Got it.
Right.
So then he didn't have a need to explain that to you. Because dielectric materials typically
Use that.
are just a factor of
You can
free
use
space
mu naught.
times whatever it is, right?
oh, right. Well, yeah, I know that.
Yeah.
So,
Yeah,
You know.
for some reason I thought I read it in the book somewhere. That it's, because I know that
There's a negative
your
sign.
your electric
The units right now.
If
permittivity
we were.
can change, and it changes with material, but
Mhm.
typically your magnetic
Sorry.
permeability stays at mu
Yeah,
naught
in free
for most
space.
materials.
For most materials, but
the ability, because that's.
he can use top then saying, hey, this is
Yeah, you know, whatever.
Yeah.
Okay. Okay.
Yeah, so just be worth it.
And permeability of free space.
You-
You have any questions?
So he would
Or-
have to give us.
Yeah.
Okay, no worries about that.
So there. So one,
And the same thing with.
so you found your,
Yeah, no, I didn't quite explain that for you. Yeah.
so you found your BMF.
Yeah, I found VMF. I did the actual math. Not the derivative portion of it yet. Okay, I'm just here dotting it through, going through, doing the actual math, right? You can, for the sake of this, you can view
So,
the 120 pi as just omega and just treat it like that until the very end, because it's just a factor, right? So you're just literally going through doing the
permeability.
integral
Yes.
of x
Clear.
of your unit vectors times some value, right? Because we're doing it with respect to x and y, right? This gets pulled out a few times, which is where that w comes from, right? Is it will cancel itself out once you actually go through the math. The biggest thing is, okay, do you know how to even do the dot product first?
Yeah. Yeah, there's a similar problem to this in the, on Canvas. And yeah, so far, like my math's been the same, it's been right. But when I was asking, so we found the VMF,
No,
the
Jay,
current in it is just that VMF divided by the internal resistance
Yes, sir.
of the wire. Okay.
correct.
And which is how you got your.
Yeah, that weird.
43.
Yeah, the weird value.
The derivative.
It's just one quick line of math that, you know,
Oh, yes, yes. Integral of J with respect to X.
yeah, no, there it is right there. Yeah, I forgot correctly that. Crazy, my bad.
You said there could be.
The displacement current.
Which is this.
Yeah, that's the displacement current density when you get.
Wait, my, okay,
Displacement current.
Got it.
The final line of math would be multiplying it by, right? Or am I going crazy? That final line of math where you, get no resistance, how'd you factor that in again? We just literally said it, I just can't remember.
The internal resistance.
Yeah,
Oh, well, yeah, you divide the EMF or
Divide it.
the resistance, right?
Yeah.
It's I and B, yeah, I equals D on here.
we put R not there for now, but I'll clean up. But yeah, so yeah, I forgot for that. Okay, real quick, okay, I forgot to mention this. I skipped it out on my work, but okay. The internal resistance of the loop, it's,
Oh, right,
yes, 3 ohms, 3 ohms.
yeah.
Okay, 3 of you apparently.
Thanks, Brandon.
How would I factor that into all this?
Wait, we found V in that.
Yeah.
So you just V, what is
I-
it? V over R equals I. Okay, cool.
That's
This was my test.
Yeah,
So why does that give us displacement current though?
You don't even know.
Say do?
Oh, it just gives us current and we know it's just displacement current because there's no electric field.
it depends, yeah, but
Okay.
it applies it, again, he's not asking for you if you can tell what current that is, he's just asking you, give me a current value.
Okay,
You were overthinking it.
well, it's
This comes back to, I don't wanna say just Ohm's law, but like our,
I would say-
our relationships, right? Because at the end of the day, voltage over resistance is what's current, right?
Mhm.
We're given the resistance of our loop, we found the voltage going across it. You just divide it by it and then you just get.
Right.
Yeah.
Why is part two instead of part one?
The biggest thing is he tests you specifically if you even know to use this relationship.
Okay.
That's the biggest test.
Well, what I mean by that is part B, second, and in most people's minds, they would do that second. You
Mhm.
get what I'm saying?
Yeah.
So if we weren't to do that second, part one sounds like it'd be kind of difficult.
I mean, they were both independent. We didn't use any.
Yeah. That's the biggest thing with these current problems is they're typically going to be independent of each other unless there's some weird way he can relate the relationships together, right?
So, I mean,
How would he relate them actually? How would he have related?
but we just did. Am I wrong? Because I mean, we found the voltage
Mhm.
and we used the resistance of the loop to find current. Right? In my opinion, that is a relation.
In what domain though?
Well, when I think of,
This is time varying, okay?
okay, that's what I was thinking.
Yeah,
Okay, time-
this is time varying.
Yeah.
How do you relate current though in phasor to get back to your magnetic? Because that's what we're given. That's what we're given originally. The magnetic field.
Current in phasor.
So we're gonna use obviously Maxwell's.
So this is, yeah, basically this is how you would relate it, okay? Assuming he gives you a problem like this, saying we'll somehow relate current to get back to your magnetic.
Got it.
How would you even do that, right? This is more so thought. I haven't seen him do this before. Okay, this is more just like food for thought, basically.
Yeah, because current equals the magnetic field intensity, which you can just solve that with the mu to get the magnetic field B. I forgot there are, but you get B and then go back to electric.
Wait,
field.
wait,
That's
just slow down and say that again.
right.
I would have to give it more thought. This is just literally me like tossing it out there.
Slow down and say what you're
Well,
saying.
we got the current, right?
Current
Is
this
only that equals H, which is the intensity, magnetic intensity, right? So B equals mu H. So if we have the permeability, we can go back to this equation with B and then find that.
Right, so what I'll probably do, in the recorded one I'm gonna do later on in the week, I'll probably just gonna do a double load problem.
Mhm.
A different stub matching question. I don't know what to do for third problem.
Could you
No.
do another one of these?
Another one of those.
Another one of these for the star roll?
Newest topic.
Yeah, Maxwell equations are rough.
Okay, fine.
They're rough, man.
So I'm gonna record myself later on at some point before Thursday, probably the weekend. Going to cover a double load problem.
Just, do you want to do it by yourself or do you want to hold one of these?
No, I'll just yeah, I'll just record it and stuff.
Your fault.
Gonna be a double load problem. a stub matching question of sorts, okay? Because the other one I want to probably do for that one is probably gonna be like, hey, give an S1 your good old friend.
Oh, man.
Hate that guy.
Yeah.
That guy. I hate that guy.
This is a great question though. I love it. It's worth 40 points too. So
It was on there, a similar question.
It's
yeah,
not part B.
Wait, I'm sorry, that was literally on our freaking test. Sorry, except for part B. What-
except for Barbie, but part B is where the fun stuff begins. So I'm gonna do a double question, probably a stub matching of sorts, maybe that one or a different one, right? Because I have another one here, and then I'll find another Maxwell's equations.
Do you want me, I sent you the, did I send you the PDF?
No,
I sent Zach. Let me send it to you. PDF.
Oh, so when it
I
comes
received
to
another.
Maxwell
test from somebody
equations,
that.
can we, I mean, you don't want to like assume anything, but to watch it. But do you want,
I don't have.
does he normally do Faraday's law?
he can do both. He's done either or. Like I've seen some tests where it's mostly Faraday stuff,
Uh-huh.
and then
You guys
actual
study
Maxwell's.
together, like in the.
Oh,
Like he
okay,
won't.
sorry, I thought,
Yeah, he won't recommend. Like he won't mix the two in one problem, right?
Trying.
At least let me think about it.
sorry, I thought that Maxwell equations were, or Faraday's law was part of Maxwell.
Study sure.
It is.
What I know.
It is. Let me rephrase what I was saying.
Probably we can do the same for this one.
Yep.
I heard exam two is supposed to be.
I heard that too, Chase said that.
Yeah.
Yeah,
Apparently exam one is the hardest.
yeah.
Yes.
Chase said that,
Yeah.
test 2 and test 3 were easier than test 1.
Dang.
Yeah.
Coming from someone who I.
No, it depends if you're using the integral form versus the differential form. That's the biggest thing. You won't ever mix the two too hard. It'll be something simple as like the question we just covered,
Mhm.
but nothing like super complex. Because I've seen problems where you have to use like 4 differential form equations just to relate like a few things here and there, and then finally get like a final answer for it. But he'll lead you though. In a question like that, where it's gonna be that heavy, he will actually lead you, okay? And the order of what you're supposed to solve the problem in would help. Okay.
So, do you?
I guess I would, overall,
Hmm?
right, chapter 6, overall. Dynamic cases where we have it's not the integral form. He said that we use the integral. Integral.
I just
form.
need that test.
Heard the number of loops, I'm guessing, right? I'm guessing if you're giving a thickness of sorts.
I guess that's what I'm trying to like
Yeah.
answer.
Yeah.
What I need to do, because I already know that if it's not static, then I'll use this. If it's static, I'll use this, right? Like that's a number one.
Yes, that part should be down pat for a majority of people, at least seeing that.
Right, but now I'm stuck like, okay, I know like this, but then this.
Let me.
When to use differential or when to use.
Sure, yeah, because he covered that and I
The
just can't remember.
biggest thing you'll know is he'll tell you there's a number of loops. If there's a number of loops, you're probably gonna be using most of those equations because those number of loops will get an n value source, right?
Yes,
That's the biggest thing. If you see some n value, you're probably gonna be looking at some equations using your loops, using the thickness of that. So when I say that the thickness is in like, he'll tell you each loop is equal to whatever thickness, right? Then that's gonna be your balance for that area
so
we're trying to find.
integral form, are you saying?
Mhm.
So loops associated with integral?
Typically, yes.
Okay.
Loops are associated with integral form. no?
Typically, because all you're saying is, hey, in this n number of loops, there's this prop behavior going on, right? If it was a Maxwell equation stuff, it would be like, here's a shape in free space. Tell me something about it.
That would be
Versus here's a coil of like X loops, or like the reason why I bring up shapes is because he'll toss you like, hey, here's a 10 loop triangle coil here. That's a test 3 question, but typically, because that's
Well, we
where
had test 2 question on test 1, so.
Yeah, so I don't know what he's doing, because if he really wants to get to like chapter 8 and 9 and 10, those are gonna be like your radar equations and stuff, which is also pretty easy, in my opinion.
And chapter 7, we haven't got through chapter 7 yet.
Really?
So do you
Yeah.
think he's gonna have like a double load for sure since it wasn't on the first test?
Most likely, well, okay. I say most likely, all it is just double loads.
You just treat the first
load, the.
You have
most
two
inward
things,
load,
okay,
like a-
here's how I would approach it, okay, not meant to cut you off. All you're doing in double load, okay, so I'm gonna go and draw it out, right?
Sweet.
So all you're doing in double load, okay, literally. I already have the freaking notation here, okay, this right here, you're gonna have some Z in small, some gamma in small, and there's another thing I'm missing right now.
We treat it like a small.
Yes.
You treat the original one as the power source and then you.
Yeah, so
you split
yeah,
them up.
okay, because the biggest thing is you're trying to convert all of this to a point where you know the voltage.
Yes.
Okay, because once we here, yeah. So basically you Z in, okay, so you shifted it, right? So at some point you have your two loads, right? Guess what? They're now at the same point in parallel, so you just add them in parallel, right?
Yeah.
Okay, so now you have a single load problem. Guess what? We should know how to do single load problems
Hope so.
by now, right? And then you just treat it like that, okay? Once when you find your V naught plus, right? At some point, okay, just work backwards. Just work backwards to whatever point you're trying to get to. And that's literally it.
Yep. At one point,
The biggest thing is for problems like these, don't get confused. What voltages he's trying to ask you for, okay? Because he will tell you, hey, find the voltage at, in this case, it's X of M, right? Which is your big, right? If you followed like the notation, right? Zn big, Zn small, right? Just careful on what you're trying to actually find here. Because people have confused themselves whenever they actually go through the math. They don't label like
Yeah.
which branch is which.
Yep.
And then they're just like, wait, which one is it now, right?
Yeah. Labeling is the best,
Yes.
best friend.
And don't be afraid to solve it symbolically first. Okay. What I mean when I say that is sometimes he'll give you not your two loads, but ZL, unknown middle load, and a voltage at some point.
Yep.
Understand how to solve that too. And always just saying, hey, treat it like a variable. Don't worry about it. Say it's some multiplied by some factor, right? Solve it through. You're gonna do a system of equations at some point. That's all it's gonna be. It's not gonna be just a straight like one line, one equation, one variable. It's gonna be like a few equations. Probably you have to substitute in here and there, but that's all it's gonna be.
Yeah.
Double loads aren't that bad. I'm still gonna cover it, but they really aren't that bad. I'd say the hardest thing on here is probably, in my opinion, probably the submatching stuff if you're not familiar with the shortcuts specifically. And it would be the Maxwell equations, all those stuff, if you're not familiar with just physics in general. Those are the two biggest things, right? So one's more like you can brute force the math there. The physics part, you have to understand it to an extent to be able to use it, right? Because the math itself, for sometimes, like as we saw here in this problem, it canceled itself out pretty easily, and that's how you're typically gonna do it. But it was also one of the easier questions too. But yeah, I'll record myself actually like doing a proper review. Was not prepared for this one at all, so
Well, we got through most of it pretty well.